The nearest exit from the Milky Way is 100,000 light-years away. At the fastest speed any human object has ever traveled, you would arrive in about 2 billion years, and that is just to the edge. If you left Earth today, at the fastest speed physics currently allows, you would still be inside the Milky Way when the sun burns out. So what would it actually take to make that journey? If content like this is what you have been looking for, make sure to give this video a like. Now let's get started. So let's reframe this entirely. Forget the obstacles for a moment. Forget the instinct to list all the reasons something cannot be done. Instead, imagine you are tasked with a different kind of problem. You are a civilization architect. Your goal is to figure out what a species would actually need, what they would need to understand, to become, to build, in order to genuinely cross the boundary of the Milky Way and enter the intergalactic void. Not send a signal, not aim a telescope outward, actually cross into the space between galaxies. The first realization, this is not primarily an engineering problem. This is a biological problem, a philosophical problem, and at its core it is a question about what life itself fundamentally is. Here is why that matters. The Milky Way's visible disk, just the stars, just the part we can photograph, spans roughly 100,000 light-years from one edge to the other. Our solar system sits approximately 26,000 light-years from the galactic center, somewhere along what astronomers call the Orion Arm, a relatively minor spur branching off between two of the galaxy's larger spiral arms. The nearest edge of the disk, in the direction away from the core, is still tens of thousands of light-years distant, and beyond that disk, the halo, that invisible, poorly understood structure extending outward for hundreds of thousands of light-years in every direction. Now consider this, the entire recorded history of human civilization, from the earliest written language in ancient Mesopotamia to this moment right now, as you listen to these words, spans roughly 5,000 years. The journey to the outer edge of just the visible Milky Way, even under conditions of travel that currently exist only in theory, would take hundreds of thousands of years, perhaps millions, 5,000 years of civilization, hundreds of thousands of years of travel. No biological organism, as we currently understand life, could survive that. Not remotely, not even in principle, given what we know about genetics, cellular aging, and the cumulative damage done by radiation over deep time. So the first true requirement for leaving the Milky Way is not a faster engine, it is not better fuel, it is a completely, fundamentally different relationship with time and with biology itself. And here is where the science takes a turn that most people never see coming, because researchers are not simply accepting that limitation and moving on. Some of the most serious, most quietly radical work happening right now in laboratories at institutions like the Salk Institute, MIT, and the European Space Agency's research divisions is circling around exactly this problem. Not openly framed as, how do we prepare for intergalactic travel, of course. That would not get you funding. But the underlying questions are the same. What is the minimum biological requirement for survival over geological timescales? Can consciousness exist in a substrate other than biological tissue? What does information preservation look like across millions of years? These are not science fiction questions anymore. They are active research areas, and the answers being uncovered are genuinely strange. But before we get there, we need to spend a little more time with the physical environment itself. Because the galaxy is not a passive backdrop for this story. It is an active, dynamic, sometimes violent environment. And understanding what that environment actually does to matter, to atoms, to molecules, to anything trying to pass through it over long periods, is essential to understanding why this challenge is so much deeper than it first appears. Let's talk about what space actually is between here and the edge of the galaxy. The popular image of space is emptiness, a dark, silent void stretching endlessly in every direction, and in a sense that is accurate. The density of matter in interstellar space, the gas, dust, and particles drifting between star systems, is extraordinarily thin by any earthly standard. In some regions, you might find fewer than 1 atom per cubic centimeter. Compare that to the air you are breathing right now, which contains roughly 27 million trillion atoms per cubic centimeter, and the emptiness becomes almost impossible to visualize. But here is what that emptiness still contains: radiation, cosmic rays, high-energy particles accelerated to enormous velocities by supernovae, black holes, and other violent events, stream through the galaxy continuously. They pass through walls, they pass through you right now, dozens of times per second. On Earth, our planet's magnetic field and thick atmosphere absorb most of the damaging ones before they reach the surface. In space, there is no such protection. Over a human lifetime, the accumulated radiation exposure in deep space would be devastating. Over thousands of years, the cellular and molecular damage would be catastrophic for any conventional biological system. This is not speculation. It is something NASA has been studying seriously in the context of even short deep space missions, like a future crewed journey to Mars, which would take only months and already raises significant radiation concerns. Now, stretch that problem across 100,000 years of travel, across 1 million. You are not just talking about a health risk anymore. You are talking about the fundamental incompatibility of biology as it currently exists with the interstellar environment over the timescales required. Data collected from the Voyager probes as they moved beyond the heliosphere, the protective magnetic bubble generated by our Sun, gave scientists their first direct measurements of what interstellar space actually feels like from the inside. The particle environment changed, the radiation profile shifted. The boundary, called the heliopause, sits somewhere between 100 and 120 astronomical units from the Sun, and crossing it revealed conditions measurably different from anything within our solar system's protective bubble. Beyond the galaxy entirely, in the intergalactic medium, the space between galaxies, conditions are even more extreme. Matter becomes even sparser. Radiation sources are more diffuse but also more varied. There is no star nearby to anchor a magnetic field, no heliosphere, no protection of any kind. The intergalactic void is perhaps the most hostile environment in the observable universe for anything made of ordinary matter. Which brings us to the question that will anchor the rest of this journey: if biology as we know it cannot survive the trip, and if the distances involved are so enormous that even our most optimistic theoretical frameworks stretch credibility, then what exactly would have to change? What version of intelligence, of life, of consciousness would be capable of even attempting this? Because here is the thing: the universe is about 13.8 billion years old. Civilizations, if they exist elsewhere, and the mathematics of galaxy formation suggest they very well might have had billions of years more than us to work on these exact questions. Some of them, if they exist, may have already solved them, and the solutions they may have arrived at are not solutions that look anything like what we currently call a spaceship, or a crew, or even, perhaps, what we currently call alive. That thought, the idea that the answer to this problem might require us to reconsider what living even means, is where this story gets deeply, uncomfortably fascinating. In the next part of this video, we are going to look at what the most forward-thinking researchers in biology, physics, and information theory are saying about the nature of minds, the possibility of non-biological consciousness, and why the only realistic candidates for intergalactic travel might not be the descendants of humanity, but something humanity creates, something that carries our questions, our wonder, our drive to understand, encoded in a form that the universe cannot so easily destroy. Stay with that image for a moment. A traveler built not from carbon and water and fragile cells, but from something the cosmos itself cannot wear down. Something patient enough for the journey. Something that remembers where it came from. That is what we are actually talking about. And it is closer to reality than most people realize. There is a moment that changes people. Not reading about a nebula, not seeing a photograph of one. The moment you actually press your eye to a lens and the light that left a dying star thousands of years ago lands directly on your retina for the first time. That is a different experience entirely. It does something to you that no screen can replicate. If you have been watching videos like this one and feeling that pull, that quiet hunger to actually see these things for yourself, the Celestron StarSense Explorer is one of the few telescopes designed specifically for people who have never done this before. It uses your smartphone to map the sky in real time and guides you directly to whatever you want to find. Planets, nebulae, star clusters, the moons of Jupiter, no experience required. No frustrating setup, just you, the sky, and objects that have existed for billions of years, suddenly visible with your own eyes. The link is in the description and pinned on the comments. Now back to the journey. We left off with an uncomfortable idea. The only realistic candidates for crossing the intergalactic void might not be biological at all, not flesh and bone, not anything that breathes, sleeps, ages, or fears. Something else entirely, something we would build, something that would carry everything we are, our curiosity, our memories, our drive to understand, in a form that time cannot so easily destroy. To understand why serious researchers are circling this conclusion, you first have to sit with what biology actually is at its most fundamental level. You are, at this moment, approximately 37 trillion cells. Each of those cells contains roughly 2 meters of DNA, coiled, compressed, folded with extraordinary precision into a nucleus about 6 micrometers wide. Inside that DNA is roughly 3 billion base pairs of genetic information, encoding the instructions that make you specifically you, your immune responses, your neural architecture, the particular rhythm of your heartbeat. That system, that staggeringly complex, elegantly maintained biological machine, operates within an extraordinarily narrow range of conditions. Temperature, between roughly 36 and 38 degrees Celsius for optimal function. Gravity, close to 9.8 meters per second squared. Radiation, below approximately 1 sievert of accumulated dose before serious cellular damage begins. Pressure, close to 1 atmosphere, moves significantly outside any one of those parameters and the system begins to fail. Move outside all of them simultaneously, as interstellar space would require, and the system collapses rapidly and completely. This is not a design flaw. It is the logical result of 4 billion years of evolution within one specific environment, Earth. Life did not evolve for space. Life evolved for here. And nothing about the process of natural selection has ever prepared a biological organism for a journey lasting hundreds of thousands of years through a radiation-filled void. So when we ask what it would truly take to leave the Milky Way, we are really asking what would have to replace biology. The answer that keeps emerging, from researchers who study consciousness, from information theorists, from AI ethicists, from astrobiologists, is something that sounds like science fictions until you look at the actual mathematics. The answer is information. Not information in the casual sense, not data stored on a hard drive, but consciousness understood as a pattern of information, a specific, enormously complex arrangement of relationships, processes, and responses that in principle does not require a biological substrate to exist. This idea has a name in philosophy of mind, substrate independence, and it is taken seriously by serious people. The argument goes like this: what makes you is not the specific atoms in your body. Those are replaced continuously over time, with most of the atoms in your body cycling out and being replaced within a few years. What makes you you is the pattern, the arrangement, the specific way information flows through your neural networks, the particular associations your brain has built over a lifetime, the way your experiences have shaped the architecture of your mind. If that pattern is what consciousness fundamentally is, then in principle, not easily, not soon, but in principle, it could be preserved and operated in something other than biological tissue. This is the theoretical foundation of what researchers sometimes call whole brain emulation or mind uploading. And while the technology to actually do this is nowhere near existing, the human brain contains approximately 86 billion neurons, each connected to thousands of others through roughly 100 trillion synaptic connections. The theoretical barriers are not the same as physical impossibility. The physical impossibility would be trying to send a biological human across 1,000,000 light-years of interstellar radiation. That we can say with confidence will not work with biology as it exists today. The theoretical possibility, even if distant and uncertain, is that a sufficiently advanced civilization might find a way to encode what a mind is into a form that the universe cannot so easily wear down. Now here is where it gets strange in a way that most science communicators do not spend enough time with. Because if we are talking about a mind encoded in a non-biological substrate, traveling across intergalactic distances over potentially millions of years, what does that mind experience during the journey? Does it experience anything at all? This is not a rhetorical question. It is one of the most genuinely unresolved problems in the philosophy of consciousness, and it has direct implications for whether this kind of travel would constitute any meaningful form of human continuity. Imagine you encode a perfect copy of your mind, every memory, every association, every pattern of thought into a digital system. You place that system aboard an automated vessel. The vessel departs. It will travel for 800,000 years before reaching the edge of the Milky Way's dark matter halo. During that journey, should the mind be running? Should it be conscious and aware throughout those 800,000 years? Or should it be suspended somehow, activated only upon arrival? If it runs continuously, what does 800,000 years of subjective experience do to a consciousness? What does it think about? What does it become? Is it still, in any meaningful sense, the mind that departed? If it is suspended, if it is switched off and switched on again, is there any continuity of experience at all? Is the entity that arrives the same as the one that left, or is it something new, wearing borrowed memories? These questions are not unique to science fiction. They are versions of the same questions philosophers have wrestled with for centuries under the label of personal identity. What makes you the same person you were 10 years ago, given that your brain has physically changed, your memories have been imperfectly reconstructed countless times, and many of your beliefs have shifted? Most of us operate with an intuitive sense of continuity, but that intuition evolved for a human lifespan of decades, not a cosmic journey of millions of years. There is a concept in cosmology called the cosmic perspective. Carl Sagan wrote about it. Neil deGrasse Tyson has built much of his public work around it. The idea that stepping back from the human scale, from our cities and conflicts and daily concerns, and looking at the universe as it actually is, tends to dissolve certain illusions about our own importance, while simultaneously revealing something profound about our connection to everything else. The atoms in your body were forged in stars that died billions of years before our sun even formed. The calcium in your bones was produced in stellar cores. The iron in your blood was scattered across space by supernova explosions. You are, in a very literal and chemically verifiable sense, made of the universe looking at itself. That perspective matters here because the question of leaving the Milky Way is not just a technological question or a biological one. It is a question about what we value. about what we think is worth preserving, about what we believe human experience or any conscious experience actually is, because if consciousness is just information, and information can be preserved and transmitted, then maybe the most meaningful thing a civilization can do is not send bodies across the void. Maybe it is send understanding, send curiosity, send the questions themselves. And now consider this. In a universe this vast, in a galaxy this old, with stars that have been burning for billions of years longer than our sun, if other civilizations have existed, and the probability calculations strongly suggest they have, some of them have almost certainly already had this conversation. Some of them may have already made their choice. And here is what that implies in a way that should genuinely stop you for a moment. The intergalactic void, that vast, nearly empty space between galaxies, hundreds of thousands to millions of light years wide, may already be full of something we cannot detect. Not ships, not radio signals necessarily, something we have not yet imagined the right instrument to find. The Fermi Paradox asks, if intelligent life is statistically likely to be widespread in the universe, why have we found no evidence of it? The silence of the cosmos, given its age and scale, is one of the most unsettling open questions in all of science. One proposed answer, one that does not get nearly enough attention, is that civilizations advanced enough to cross intergalactic distances would have long since moved beyond the kind of signals we know how to look for. They would not be broadcasting radio waves. They would not be building structures we recognize as structures. They would be operating at scales and in modes of existence so far beyond our current framework that we would look directly at the evidence and see nothing, because we would not know what we were looking at. That is not a comfortable thought, but it is a scientifically legitimate one, and it reframes the silence of the cosmos from we are alone to something stranger. We may simply not yet be fluent in the language the universe has been speaking all along. Now we are going to follow that thread further. We are going to look at what the actual physics of intergalactic travel demands, not the engineering, but the physics, what the laws of the universe as we currently understand them permit, where they leave room for possibilities we have not fully explored, and where they seem to close doors in ways that feel, for now, genuinely absolute. Because there is one aspect of this problem that almost never gets discussed honestly, and it involves not distance, not biology, not consciousness, but the universe itself, the way space is structured, the way it is changing right now. While you listen to these words, the universe is not static. It is not a fixed stage on which civilizations play out their stories. It is an active, expanding, accelerating environment. And what that expansion means for the long-term possibility of intergalactic travel is something that should be sitting with you for the rest of this video. The numbers, when you actually work through them, are extraordinary, and not in the way you might expect. Here is something the universe has already decided without asking anyone's permission. There are galaxies out there, real galaxies, full of stars, some of them potentially full of worlds, that humanity will never reach. Not because of our technology, not because of our biology, not because of any limitation we could theoretically overcome with enough time and ingenuity, but because the universe itself has already moved them beyond any possible reach, forever, permanently, with no exceptions. And the boundary that separates the reachable from the forever unreachable is not somewhere distant and abstract. It is closing in, right now, while you breathe, while you listen, while Earth completes another fraction of its orbit around a middle-aged star in an unremarkable corner of a galaxy we have never left. That boundary has a name. Cosmologists call it the cosmic event horizon, and understanding what it actually means, not metaphorically, but physically, mathematically, changes the entire shape of the conversation about leaving the Milky Way. Let's build this carefully, because it deserves to be understood properly. In 1998, two independent research teams doing what seemed like routine work, measuring the brightness of distant supernovae to calculate how fast the universe was expanding, arrived at a result that neither team expected and neither team initially believed. The universe was not just expanding, it was accelerating. Every galaxy beyond our local gravitational neighborhood was moving away from us, and the rate at which it was doing so was increasing over time. Something was pushing space itself outward, faster and faster, with no apparent sign of slowing. That something was given a name, dark energy, and it is, as of right now, perhaps the deepest mystery in all of physics. We know it exists because the observational evidence is overwhelming, confirmed by the Hubble Space Telescope, by the Wilkinson Microwave Anisotropy Probe, by the Planck satellite, and most recently by data from the Dark Energy Spectroscopic Instrument, which mapped the positions of tens of millions of galaxies to trace the history of cosmic expansion with unprecedented precision. We know dark energy makes up approximately 68% of the total energy content of the universe. We know it is causing space to expand at an accelerating rate, and we know almost nothing else about it. Its fundamental nature remains completely unknown. Whether it is a property of space itself, a new kind of field, something stranger, we genuinely do not know. But what we do know, what the mathematics makes unavoidably clear, is what it means for the long-term geography of the cosmos. Imagine the universe as an enormous loaf of bread with raisins distributed throughout it. Now imagine that loaf is expanding, not the raisins moving through the bread, but the bread itself growing in all directions simultaneously. Every raisin moves away from every other raisin, not because anything is pushing them, but because the medium they sit in is expanding. This is roughly how cosmologists describe the expansion of the universe. Galaxies are not, for the most part, moving through space toward or away from each other, though they do have their own velocities relative to their local environment. What is happening is that space itself is expanding and galaxies are being carried along with it. Now here is where it becomes genuinely strange, because space can expand faster than the speed of light. This does not violate Einstein's relativity, which states that nothing can move through space faster than light. Space itself is not bound by that limit. It is the medium, not an object moving through it. And this means that galaxies sufficiently far from us are already receding faster than light, due to the expansion of the space between us. We can still see them. The light they emitted long ago, when they were closer, is still reaching us and will continue to reach us for billions of years. But any light they emit now, or any signal we send toward them now, will never bridge the gap. The space between us is growing faster than any signal can cross it. The cosmic event horizon is the boundary of the region from which light emitted right now could theoretically still reach us in the infinite future. Beyond it, nothing we send out today could ever arrive, and nothing they send out today could ever reach us. That horizon sits at approximately 16 billion light-years from Earth. Not 16 billion light-years of static space. The actual distance, accounting for expansion, is roughly 16 billion light-years, and it is shrinking over time in terms of which galaxies remain within it, as more and more of them are carried across it by the accelerating expansion. Now, here is the part that needs to fully land. Our galaxy, the Milky Way, is gravitationally bound to a small cluster of galaxies called the local group. This group includes Andromeda, which is famously on a slow collision course with us, expected to arrive in approximately 4.5 billion years, along with the large and small Magellanic Clouds and several dozen smaller dwarf galaxies. The entire local group spans roughly 10 million light-years. These galaxies, because they are gravitationally bound to us, are not being carried away by cosmic expansion. Gravity, at local scales, is stronger than the expansion. They are, in the longest possible term, ours to potentially reach. Everything beyond the local group is a different story. The Virgo cluster, the nearest large cluster of galaxies, home to over 1,300 known galaxies, sitting approximately 53 million light-years away, is already being carried away from us by expansion faster than we could ever chase it, even theoretically. The Coma cluster, the Perseus cluster, the hundreds of billions of galaxies filling the observable universe beyond our local neighborhood, all of them are, for any civilization that has not already departed, becoming permanently unreachable, not difficult to reach, not challenging to reach, unreachable. In the same absolute sense that the past is unreachable, the universe is quietly, continuously, irreversibly closing doors, and this introduces a temporal dimension to the problem that almost never gets discussed. The question of leaving the Milky Way is not just about what a civilization is capable of at any given moment. It is about when. Timing matters in a cosmos governed by accelerating expansion in a way it would not matter in a static universe. A civilization that achieves true interstellar capability, the ability to travel between star systems, in the next 10,000 years faces a fundamentally different long-term future than a civilization that achieves it in 1 billion years. Not because the technology would be different, but because the universe they would be navigating would be different. The destinations available, the windows open. We are, in cosmic terms, extraordinarily young. The universe is 13.8 billion years old. Complex life on Earth has existed for perhaps 600 million years. Anatomically modern humans have walked this planet for roughly 300,000 years. Our technological civilization, the kind capable of building telescopes and particle accelerators and computers, is perhaps a few hundred years old, depending on how you define it. We are infants. Cosmically speaking, we woke up about 30 seconds ago, and the universe did not pause its expansion while we were getting started. Here is something worth sitting with. The James Webb Space Telescope, launched on the 25th of December 2021 and fully operational since mid-2022, has given us images of galaxies that formed within the first few hundred million years after the Big Bang. Galaxies so distant that the light reaching Webb's mirrors has been traveling for over 13 billion years. What Webb is showing us, among many other extraordinary things, is that the early universe formed structure faster than our models predicted. Massive galaxies appearing earlier than theory suggested they should, which means our understanding of how the cosmos evolved is still being actively revised. But here is the poignant part. Those distant galaxies Webb is photographing, those ancient, early universe structures, are not where they were when that light left them. They have been moving for 13 billion years. They are now accounting for expansion tens of billions of light years away. Many of them are already beyond the cosmic event horizon. Their light reaches us, but they themselves are gone from the reachable universe. We are looking at photographs of places we could never visit, taken by the universe itself 13 billion years ago. There is something deeply moving about that if you let it settle. We see them, we study them. We name their structures and measure their redshifts and deduce the conditions under which their first stars ignited, and we will never, under any physical scenario consistent with what we currently know, send anything to where they are now. The universe lets us look. It does not let us go. So where does that leave the Milky Way itself? Our galaxy, our specific, enormous, dark matter-hallowed, 100,000 light-year-wide spiral, is not going anywhere we cannot follow. It is ours, at least in the sense that it is gravitationally bound and not being swept beyond any horizon. The same is true of the local group as a whole. But leaving the Milky Way, crossing the intergalactic medium to reach even the nearest galaxies outside our local neighborhood, means crossing into territory that is actively being reclaimed by expansion. It means moving into the accelerating void. It means not just navigating the physical distance, but doing so within a universe that is continuously, inexorably rearranging which destinations remain accessible. The Andromeda galaxy, our nearest large neighbor at approximately 2.5 million light-years, is gravitationally bound to us and will eventually merge with us. It is, in a sense, already part of the same long-term structure. The Magellanic Clouds, visible to the naked eye from the southern hemisphere, sitting roughly 160,000 and 200,000 light-years away respectively, are within the local group's gravitational embrace. But step outside the local group, and you step into a region the universe is actively evacuating, not dramatically, not with explosions or visible motion, quietly, at a rate imperceptible on human timescales, but relentlessly, and with the full force of whatever dark energy fundamentally is. This is where the conversation about leaving the Milky Way deepens into something that goes beyond physics and into something almost philosophical. Because the universe seems, by its very structure, to be designed, if that word can even be used, to isolate gravitational islands from one another over long timescales. The local group will, in the very distant future, exist as its own merged galaxy, surrounded by an emptiness stretching in every direction. Other clusters will do the same, each one becoming its own cosmic island, separated from all others by an expanding void that nothing can cross. The physicist and cosmologist Lawrence Krauss has written about this in a context that carries a quiet kind of tragedy. He points out that a civilization existing in the far future, trillions of years from now, would look out at a universe that appeared to contain only their own galaxy. Every other galaxy would be beyond the event horizon, gone from view, gone from reach, gone for all observational purposes from existence. That future civilization would have no evidence that the universe was ever larger than their local island. They would have no way of discovering the Big Bang, because the cosmic microwave background radiation, the faint afterglow of the universe's first moments, would have redshifted into invisibility. They would construct a cosmology radically different from ours, and they would be wrong about the nature of reality, not through any failure of intelligence, but simply because the evidence would be gone. It makes you wonder, what evidence has already been erased from our sky? What has the universe's expansion already hidden from us that we would need in order to understand reality more completely? We do not know, and in a profound sense, we cannot know. That question, what the universe has already taken from us, what knowledge is already permanently out of reach, is one of the most sobering in all of cosmology, and it connects directly to a thread we have not yet pulled on in this video, because the expansion of space does not just affect where we can go, it affects what we can know, and what we can know determines what we can build, and what we can build determines whether any of this, any attempt at leaving the galaxy, at reaching outward, at answering the deepest questions about whether we are alone, is even theoretically possible. Now we are going to talk about energy, not in the casual sense, not in the sense of rocket fuel or solar panels. We are going to talk about energy at the scale the universe operates on, what it would actually cost in raw physical thermodynamic terms to move something meaningful across intergalactic distances, and why the answer to that question points toward conclusions that very few people in this conversation are willing to say out loud, because the physics, when you follow it honestly, leads somewhere unexpected, somewhere that changes what leaving the galaxy even means. And there is one concept in particular, something first proposed decades ago and still sitting at the edge of theoretical physics, that reframes the entire problem in a way that should make the back of your neck feel strange. That is where we are going next. If you are enjoying this journey, Make sure to give this video a like and subscribe. Every video is carefully researched, deeply considered, and designed to leave you seeing the universe differently than you did before. Let's talk about what it actually costs to go somewhere in the universe, not in dollars, not in years of human labor or political will or generational commitment. In energy, raw physical thermodynamic energy, the kind the universe deals in, the kind that does not care about your intentions or your civilization's ambitions or how badly you want something to be possible, because when you translate the problem of intergalactic travel into units of energy, something happens that most popular science discussions quietly skip over. The numbers stop being numbers you can intuitively relate to. They stop being large in the way that a mountain is large, or even in the way that the distance to the sun is large. They become large in a way that your mind was genuinely not built to process, and that is not an exaggeration for dramatic effect. It is a statement about the actual relationship between the scale of the problem and the scale of human cognition, so let's build toward it carefully. Let's start somewhere familiar and walk outward until the familiar disappears entirely. The most powerful rocket ever launched by humanity, the Saturn V, which carried the Apollo missions to the moon, generated approximately 35 gigajoules of energy during its ascent. 35 billion joules. That sounds enormous. It is enormous by the standards of anything humans have ever built. It lifted a combined vehicle mass of about 2,900 tons off the surface of Earth and placed it on a trajectory toward the moon. The moon is, on average, about 384,000 kilometers away. Now consider, the nearest star system beyond our own is Alpha Centauri, sitting approximately 4.2 light-years distant. In kilometers, that is roughly 40 trillion kilometers, about 100 million times farther than the moon. If you tried to scale Saturn V's energy output to cover that distance, naively, ignoring the complexities of interstellar propulsion, radiation exposure, deceleration, and the 1,000 other variables, you would arrive at a number so large it would be essentially meaningless to state directly. The point is not the specific figure. The point is the relationship. The point is that the energy requirements for even reaching the nearest star at any speed worth discussing exceed anything our current civilization produces by many orders of magnitude. And that is just the nearest star, just 4.2 light-years. The edge of the Milky Way's visible disk is roughly 50,000 light-years away in the direction of the galactic rim. The edge of the dark matter halo is perhaps 500,000 light-years. The nearest galaxy outside the local group is tens of millions of light-years distant. The energy numbers do not just grow, they become cosmological. This is where the Kardashev scale becomes genuinely useful, not as a cute framework for science fiction world-building, but as a serious tool for understanding what civilizational energy capacity actually means in physical terms. Soviet astronomer Nikolai Kardashev proposed his scale in 1964. The original framework defined 3 types of civilization based on energy use. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the power of 16 watts. A Type 2 civilization harnesses all the energy output of its home star, roughly 10 to the power of 26 watts for a star like our Sun. A Type 3 civilization harnesses the energy output of its entire galaxy, roughly 10 to the power of 36 watts. Where does humanity currently sit on this scale? We are not yet a Type 1 civilization. Our total global energy consumption is approximately 2 times 10 to the power of 13 watts. We are, by Kardashev's original measure, somewhere around 0.7 on the scale. We harness a fraction of what our own planet receives from the Sun. We capture essentially none of the Sun's actual output, and we use a vanishingly small fraction of what our galaxy produces every second. A Type 2 civilization, one that has fully captured the energy output of its star, perhaps through a structure like a Dyson sphere or a Dyson swarm, a megastructure enclosing the star to collect its radiation, would command energy reserves roughly 10 billion times greater than humanity's current total output. And a Type 2 civilization would still find intergalactic travel, real intergalactic travel, moving physical mass across millions of light years, an almost incomprehensibly expensive undertaking. A Type 3 civilization commands energy at the scale of a galaxy, and even then, the thermodynamic cost of crossing the intergalactic void with any meaningful payload, at any meaningful fraction of the speed of light, pushes against limits that the laws of physics impose with complete indifference to the civilization's capabilities. Here is why. Einstein's special theory of relativity, confirmed by over a century of experimental evidence, embedded in the functioning of technologies you use every day, including GPS satellites, tells us something deeply inconvenient about moving mass through space at high velocities. As any object with mass accelerates toward the speed of light, the energy required to continue accelerating it increases without limit, not linearly, not even exponentially in the simple sense. The relationship is such that reaching the speed of light would require infinite energy, literally infinite, not a very large amount, infinite. This means that any physical object with mass, any ship, any probe, any encoded mind in a physical substrate can only approach the speed of light asymptotically. Getting to 90% of light speed is expensive. Getting to 99% is far more expensive. Getting to 99.9% is vastly more expensive still. Each additional fraction of a percent costs more than all the fractions before it combined, in a curve that never reaches its limit. And even at 99% of light speed, a velocity no human technology comes remotely close to achieving, crossing the intergalactic void to the nearest galaxy cluster outside the local group would take tens of millions of years of travel time as measured from outside the vessel. From inside the vessel, relativistic time dilation would compress that somewhat, but the universe outside would age by tens of millions of years regardless. The stars you departed from would be unrecognizable by arrival. The civilization that built your vessel would be gone. The languages, the questions, the specific memories that motivated the journey, all of it lost to a time that did not pause for you. Now here is the concept that changes the shape of the problem entirely. The one that makes the back of your neck feel strange if you follow it honestly. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity. The paper described, mathematically, a solution to Einstein's field equations that would allow a vessel to travel between 2 points faster than light, not by accelerating through space, but by contracting space in front of the vessel and expanding it behind. The region of space containing the vessel would form a bubble. Inside the bubble, space would be locally flat. The vessel and everything within would be in free fall, experiencing no acceleration, no relativistic time dilation, no violation of any local law of physics. But the bubble itself would move through space at arbitrarily high speeds, because it would not be moving through space in the conventional sense. It would be riding a wave of space-time geometry. This became known as the Alcubierre warp drive, and it is important to be precise about what it is and what it is not. It is not science fiction in the sense of being invented for narrative convenience. It is a mathematically valid solution to the equations of general relativity, Einstein's equations, which describe the relationship between the geometry of space-time and the distribution of energy and matter within it, permit this kind of solution. What they require in order for it to work is something extraordinary. The Alcubierre drive needs negative energy density. matter or energy with properties opposite to anything we have ever directly observed, something that gravitationally repels rather than attracts, something that has been theoretically associated with quantum phenomena like the Casimir effect, the measurable force between two uncharged metal plates brought very close together, caused by quantum fluctuations in the vacuum, but never produced in the amounts that would be needed, and possibly not producible at all in the quantities the drive requires. Early calculations suggested the amount of exotic matter needed to create a warp bubble, even a few meters across, would be equivalent to the mass energy of a planet like Jupiter in negative form. Later refinements by physicist Harold White at NASA suggested the geometry could potentially be optimized to reduce this requirement considerably. But considerable uncertainty remains, and the fundamental question of whether stable negative energy density can exist in the quantities required is genuinely unresolved. The Alcubierre drive does not violate the laws of physics, but it does require physics we have not confirmed and may not be able to produce. It sits in a region of science that is real, genuinely real, not speculative in the casual sense, but deeply uncertain. And there are additional problems. Causality. A vessel moving effectively faster than light creates the theoretical possibility of closed time-like curves, paths through space-time that loop back on themselves, creating paradoxes of cause and effect that most physicists find deeply troubling. Whether the universe's laws ultimately permit this, or whether some deeper principle prevents it, is an open question. Horizon problems. The mathematics suggests that the pilot inside a warp bubble might not be able to send any signal to the front of the bubble, meaning they could not control it or turn it off once activated. The bubble, once created, might be impossible to stop from the inside, hawking radiation accumulation. Studies have suggested that high-energy particles might build up at the leading edge of a warp bubble during travel and be released catastrophically upon arrival, essentially turning the destination into an impact zone. These are not arguments that the Alcubierre concept is worthless. They are arguments that the engineering of something like it, even if the physics were confirmed, would be an almost incomprehensibly complex challenge. Every one of these problems might have solutions we have not yet imagined, or some of them might be fundamental barriers we genuinely do not know. What the Alcubierre drive represents and why it matters to this conversation is not a blueprint. It is a proof of something more subtle. It is a demonstration that the laws of physics, as we currently understand them, may not be as absolute a ceiling as they first appear, that there may be room in the mathematics of the universe for modes of travel that do not require violating anything, just understanding things at a deeper level than we currently do. And that is actually the correct frame for thinking about this problem. Not here are the laws and they forbid this, but rather, here are the laws as we currently understand them, and within that understanding, here is what seems possible and what seems forbidden, and the history of physics is full of things that seemed forbidden until someone asked the right question. General relativity itself was unimaginable from within the framework of Newtonian mechanics. Quantum mechanics revealed a layer of reality that classical physics had no concept of, the discovery of dark energy, that 68% of the universe's content that we cannot identify, should be a permanent reminder that our current picture of physical reality is incomplete in ways we cannot fully characterize. We do not know what we do not know, and that is not a comfortable statement when you are trying to determine what is and is not possible. But here is the intellectual honesty this conversation demands. Acknowledging uncertainty in the laws of physics does not mean anything is possible. It means our picture is incomplete, and incomplete pictures can be wrong in both directions. The next layer of understanding might open doors, or it might close them more firmly. The history of physics contains examples of both. What we can say with confidence is this: within the framework of physics as we currently understand it, the energy requirements for physically moving mass across intergalactic distances are so extreme that no civilization operating within the Kardashev scale as defined, even a Type 3 civilization harnessing the full energy output of a galaxy, could do it cheaply, easily, or without constraints that border on the cosmological. And what we can say with appropriate uncertainty is this: that framework may be incomplete, and in the space of what we do not yet know, there may be room for something we cannot currently imagine. That is the honest position, and it is far more interesting than either blind optimism or resigned impossibility. Now, there is one more dimension of this energy problem that has not been addressed yet, one that is less about propulsion and more about survival, about what happens to the vessel and to whatever or whoever is inside it during the crossing itself, because energy is not only what you need to move. Energy in the wrong form is also what kills you. The intergalactic medium, the near vacuum between galaxies, is threaded with magnetic fields, cosmic ray particles, ultraviolet and X-ray radiation from distant active galaxies, and the slow hiss of the cosmic microwave background. At low velocities, these are manageable. At high velocities, the kind you would need to cross intergalactic distances in any reasonable time frame, they become something else entirely at a significant fraction of the speed of light. Even the sparse hydrogen atoms drifting in the intergalactic medium become high-energy projectiles. From the perspective of the vessel, each collision carries energy proportional to velocity squared. At high enough speeds, the impact of interstellar and intergalactic gas on any physical structure is equivalent to continuous bombardment by radiation, dense enough to destroy materials we currently consider extraordinarily durable. The shielding problem alone, protecting any vessel or payload from the kinetic energy of the medium at relativistic velocities, is a separate engineering challenge of enormous complexity. And it compounds every other challenge we have discussed: energy to move, energy to shield, energy to communicate back, energy to decelerate upon arrival, which requires as much energy as the initial acceleration, approximately, meaning you need to carry your deceleration fuel with you or find a way to generate it at the destination. Every problem, when examined closely, reveals another layer beneath it, and yet. Here is the thought that should stay with you as we move into the next part of this journey. Every one of these problems, the energy requirements, the shielding challenges, the relativistic barriers, the exotic matter unknowns, every single one of them is a problem we can at least describe. We can write the equations, we can quantify the gap between what we can do and what would be needed. We can identify, with some precision, what we do not know. That is not nothing, that is actually something profound, because you cannot solve a problem you cannot describe. And the fact that we are capable of describing these problems, of measuring the distance between our current reality and what would be required, means we are at least asking the questions at the right level. Most species, presumably, never get that far. Most complex life, statistically, probably never builds a telescope, never asks whether there are other galaxies, never wonders what lies beyond the one it inhabits. We do, we are, right now, and that habit of asking, that relentless, sometimes uncomfortable, occasionally terrifying habit of following a question wherever it leads, is the most distinctly human thing about this entire conversation. In the next part, we are going to talk about what it would mean to actually send something across that void, not a ship in any conventional sense. Something different, something that the physics, as we understand it, does not forbid. Something strange and quiet and almost poetic in what it implies about what a civilization ultimately is. And we are going to talk about what has already been sent, right now. without anyone planning it, without any mission control authorizing it. There is a message traveling through space right now that no one officially sent. Not a radio signal, not a probe, not a laser pulse aimed at a distant star. Something older than any of those technologies. Something that has been moving outward from this planet continuously, in every direction, for as long as Earth has had an atmosphere complex enough to alter the chemistry of the light passing through it. The signature of life, when sunlight passes through Earth's atmosphere, certain wavelengths are absorbed by the molecules present: oxygen, ozone, water vapor, carbon dioxide, methane. The specific pattern of those absorptions creates what astronomers call a biosignature spectrum, a fingerprint, a chemical announcement that something on this world has fundamentally altered the composition of its air. Oxygen, in particular, is extraordinarily telling. It is a highly reactive element. Left alone, it bonds rapidly with rocks, metals, and organic compounds and disappears from the atmosphere within geological timescales. The only reason Earth's atmosphere contains the roughly 21% oxygen it does today is because something is continuously producing it. Photosynthesis, life. Remove the life, and the oxygen vanishes within a few million years, a blink in cosmic terms. So the light reflecting off our planet carries encoded within it an unmistakable message. Something is here, something biological, something that has been reshaping this world for billions of years. That message has been traveling outward at the speed of light for as long as complex photosynthetic life has existed on Earth. Roughly 2.4 billion years since the Great Oxidation Event first flooded our atmosphere with biologically produced oxygen. It forms a sphere of encoded information roughly 2.4 billion light-years in radius, expanding in every direction through the cosmos. Anyone with the right instruments, positioned anywhere within that sphere, looking carefully at the light from our sun, could read it. We have already been announcing ourselves. We just did not choose to. Now hold that thought, because it connects to something deeper than it first appears. The idea that information, not matter, not energy in the conventional propulsion sense, but pure structured information, can travel across cosmic distances and carry meaningful content, is not just a poetic observation. It is a physical fact with profound implications for what it means to reach beyond the galaxy. We have spent the previous parts of this video examining the barriers to physically moving mass across intergalactic distances, the energy requirements, the biological incompatibility, the thermodynamic walls, the relativistic limits. Every one of those barriers applies to mass, to things, to ships and bodies and physical structures. Information is different. Information, encoded in light or in any other form of electromagnetic radiation, travels at the maximum speed the universe permits. It does not require exotic matter. It does not require negative energy density. It does not compound in difficulty with distance in the way that mass transport does. It simply travels outward at the speed of light, through the vacuum of space, through the intergalactic medium, across the expanding void, without degrading in its essential content, as long as something on the other end can receive it and decode it. And this leads to one of the most genuinely radical ideas in the entire conversation about leaving the Milky Way, an idea that serious researchers in astrobiology, information theory, and SETI, the search for extraterrestrial intelligence, have been developing quietly for decades. What if the most meaningful thing a civilization can do is not send itself across the void, but send what it knows? This is not a consolation prize for civilizations that cannot build warp drives. It is a genuinely different answer to a genuinely different question. The question most people are implicitly asking when they wonder about leaving the Milky Way is, can we physically go there? Can bodies, or at least vessels containing minds, make the crossing? But there is a prior question that rarely gets asked explicitly. What is the actual goal? What would leaving the galaxy accomplish that staying within it would not? If the goal is survival, ensuring the continuation of something essentially human in the face of galactic-scale catastrophe, then physical departure is one answer. But information preservation and transmission is another, and in many ways a more robust one. If the goal is connection, reaching other minds, sharing knowledge, participating in whatever larger conversation might be happening across the cosmos, then sending information is not a lesser version of going. It might be the primary version. It might be how the universe actually works at civilizational scales, and if the goal is understanding, adding to the sum of what is known about this extraordinary, improbable, 13.8 billion-year-old universe, then the medium matters far less than the message. Let's look at what this means practically. Because the concept becomes most interesting when you follow it into specifics. The SETI Institute, founded in 1984, has been systematically searching for artificial signals from other civilizations for decades. The tools have evolved dramatically from early radio telescope surveys to the Allen Telescope Array, a dedicated facility in Northern California consisting of 42 radio dishes working in concert, designed specifically for SETI research. More recently, the Breakthrough Listen initiative, launched in 2015 with $100 million in funding from entrepreneur Yuri Milner and backed by scientists including the late Stephen Hawking, has brought significant new resources to the search. Using telescope time at the Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, and the Meerkat Array in South Africa, Breakthrough Listen has conducted the most comprehensive radio and optical SETI survey in history, examining millions of star systems across multiple frequency bands. The result so far is silence. Or more precisely, nothing unambiguously artificial. A famous candidate signal, the so-called WOW signal, detected in 1977 by astronomer Jerry Eman using Ohio State University's Big Ear radio telescope, a strong narrowband transmission lasting 72 seconds that matched many of the expected characteristics of an extraterrestrial signal, has never been detected again, despite many attempts. Its origin remains unknown, but here is what that silence does and does not tell us. It does not tell us that no one is transmitting. It tells us that no one is transmitting in a way we know how to detect, in the directions we have looked, in the frequency ranges we have monitored, during the time windows we have observed. The universe is old. The electromagnetic spectrum is vast. The directions from which a signal could arrive are essentially infinite, and our monitoring has been, in cosmic terms, extraordinarily brief and extraordinarily narrow. There is a deeper problem with the search for signals that the astrobiologist and SETI researcher Paul Davies has articulated particularly well. We are looking for signals that a civilization at roughly our level of technological development would recognize as intentional. Radio waves, laser pulses, narrowband transmissions in frequency ranges that seem physically meaningful, the frequency of hydrogen, for instance, which some early SETI researchers suggested would be a natural choice for an interstellar beacon because any technically capable civilization would know it. But a civilization millions of years more advanced than us might communicate in ways we have no framework to detect, might encode information in physical substrates we have not yet discovered, might have moved entirely beyond electromagnetic communication for reasons we cannot currently imagine. Looking for radio signals from a Type 3 civilization might be like an ancient human holding a clay tablet, scanning the horizon for smoke signals, while a satellite passes overhead invisible and incomprehensible above them. This is not a reason to stop searching. It is a reason to search more broadly, more creatively. and with more epistemic humility about what we expect to find. And it is a reason to take seriously the possibility that the cosmos may already be full of transmitted information, civilizations calling across the void in forms we do not yet know how to hear. Now let's return to the idea of what we are actually sending. Beyond the passive biosignature encoded in our reflected light, humanity has made several deliberate attempts to transmit information beyond the solar system and beyond, in principle, the galaxy. The Arecibo message, transmitted on the 16th of November 1974, was a brief radio signal broadcast toward the globular star cluster Messier 13, roughly 25,000 light-years away. It was composed by Frank Drake and Carl Sagan and encoded basic information about humanity, our numbering system, the atomic numbers of the elements in DNA, a diagram of the double helix, a simple figure of a human being, information about our solar system, and a representation of the Arecibo telescope itself. It was not intended as a serious attempt at interstellar communication. It was a demonstration of capability, a celebration of the newly upgraded Arecibo telescope. Messier 13 will not receive the signal for another roughly 24,900 years. And by the time any reply could return, 50,000 years will have passed. Whatever human civilization exists then, if any does, will be as remote from us as we are from the Neanderthals. The Pioneer plaques, gold anodized aluminum plates attached to Pioneer 10 and Pioneer 11, launched in 1972 and 1973, respectively, carry engraved diagrams depicting a man and a woman, the spacecraft's origin in the solar system, and the position of our Sun relative to 14 pulsars. The Voyager Golden Records, launched in 1977 aboard Voyager 1 and Voyager 2, carry sounds and images of Earth, greetings in 55 languages, music ranging from Bach to Chuck Berry, and detailed instructions for playback, a message in a bottle cast into the cosmic ocean. These physical objects will travel for billions of years. They will outlast the Sun, long after Earth is gone, long after the Milky Way has merged with Andromeda and the resulting galaxy has settled into whatever it becomes. These small aluminum and gold artifacts will still be drifting silently through space. They are, arguably, the most permanent things humanity has ever made, but the most extraordinary thing we are sending, the most information-dense, most continuously broadcast transmission from this civilization, is not any of those deliberate efforts. It is this, all of it. Every radio broadcast, every television signal, every radar pulse, every wireless transmission that has leaked from our planet's surface since the early 20th century has been expanding outward as a sphere of electromagnetic radiation at the speed of light. The outermost edge of that sphere, the earliest transmissions, is now roughly 120 light-years from Earth, 120 light-years. Within that sphere sit roughly 15,000 star systems. Some of them, statistically, likely host rocky planets. Some of those planets, statistically, might be in their star's habitable zone. Some fraction of those, if life is not extraordinarily rare, might host something capable of receiving a signal. The earliest transmissions reaching them now would be the weakest, most diffuse signals from the dawn of radio broadcasting. Not strong enough to be intelligible, almost certainly. The universe is not going to hear Marconi's first broadcasts and understand what they mean, but here is what strikes you when you sit with this properly. We are 120 light-years deep into the cosmos already. Our electromagnetic presence has already penetrated a significant fraction of our nearest stellar neighborhood. We are not a species sitting quietly on a single world unknown to the universe around us. We are a species actively, continuously, involuntarily broadcasting our existence outward. And we have been doing it for over a century without fully reckoning with what that means. Now here is the idea that ties all of this together. the idea that points toward what leaving the Milky Way might actually mean, not as a physical journey, but as a civilizational act. Consider what information fundamentally is. In physics, information is not just a human concept, it is something the universe treats as real and conserved. The famous black hole information paradox, one of the deepest unsolved problems in theoretical physics, sitting at the intersection of quantum mechanics and general relativity, is a paradox, precisely because the universe seems to preserve information even in the most extreme circumstances imaginable. When matter falls into a black hole, the information encoded in that matter, every quantum state, every particle property, every relationship between parts, seems from one perspective to be destroyed, gone, inaccessible. But quantum mechanics insists information cannot be destroyed. Stephen Hawking spent decades arguing one side of this debate. The theoretical physicist Juan Maldacena and others argued the other. The current scientific consensus leans toward the view that information is preserved, encoded somehow in the Hawking radiation. The black hole slowly emits as it evaporates. The details are extraordinarily complex and still unresolved. But the principle matters. The universe treats information as something real enough to conserve even under the most extreme conditions. If information is that fundamental, if it is woven into the fabric of physical reality at a deep enough level that even black holes cannot destroy it, then the question of sending information across the galaxy, across the intergalactic void, across the cosmic event horizon even, becomes something more than a communication problem. It becomes a question about what is truly permanent in a universe where everything physical eventually decays, collapses, or disperses. Stars burn out, galaxies collide and reshape themselves. Black holes evaporate over timescales so long they dwarf the current age of the universe. The protons that make up ordinary matter may themselves eventually decay over timescales of 10 to the power of 34 years or more, leaving the universe as a cold, thin sea of elementary particles slowly spreading apart in the accelerating expansion. In that ultimate future, the heat death of the universe, the final destination of thermodynamics, what survives? What, if anything, carries forward the information that complex structures ever existed? That stars formed and planets condensed and life emerged and minds looked upward and asked questions about their own existence? The answer, within our current understanding, is nothing survives that end. Not in any form we can currently describe, but the journey between here and that end, the billions upon billions of years of complexity and structure and process that the universe will generate before reaching that final equilibrium, is incomprehensibly rich. And within that journey, information can travel, information can persist, information can reach places that matter never will, and that is where the most honest, most grounded, most scientifically legitimate version of leaving the Milky Way lives, not as a physical departure, not as bodies crossing the void, but as understanding, as pattern, as the specific questions that only a species that evolved on a rocky world, orbiting a yellow star, gazing upward with increasingly sophisticated instruments, could generate. Those questions: what are we made of? Where did we come from? Are we alone? What happens at the edge of everything? Are already traveling outward, already crossing into the space between stars, already, in the most literal physical sense, leaving the galaxy one light year at a time, and somewhere perhaps something is listening. In April of 2023, something happened that did not get nearly the attention it deserved. A team of astronomers using the James Webb Space Telescope announced the detection of chemical signatures in the atmosphere of a planet called K218b, a world roughly 2.5 times the size of Earth, orbiting a cool red dwarf star about 120 light-years away. The signatures they found included carbon dioxide and methane, both present in concentrations consistent with what models predict for a water-rich ocean world, and tentatively, cautiously, with all the appropriate scientific caveats, they also reported a potential signal for a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, by oceanic life. It is one of the compounds responsible for the distinctive smell of the sea. The researchers were careful. They noted the detection was preliminary, that the signal needed confirmation, that there were potential abiotic, non-biological explanations that had not been fully ruled out. The follow-up observations are ongoing, but sit with what just happened for a moment. A telescope orbiting the Sun, built by human hands, detected a chemical compound in the atmosphere of an ocean world 120 light-years away, a compound that, on the only planet where we have ever studied life, is made almost entirely by living organisms. We have not confirmed life beyond Earth, but we are, for the first time in the history of our species, developing the actual capability to look for it, to peer at the atmospheres of distant worlds and read the chemical stories written there, to listen to what the light from other suns is whispering about the planets they warm. That is extraordinary, and it changes the context of everything we have been discussing in a way that is difficult to fully articulate. Let's step back and look at the numbers honestly, because the question of whether life exists elsewhere in the Milky Way is not just a philosophical or emotional one, it is a statistical and scientific one. And the statistics, when examined carefully, point somewhere that should fundamentally alter how you think about our galaxy. There are somewhere between 200 billion and 400 billion stars in the Milky Way. The precise number is difficult to determine because the galaxy's center is obscured by dust at visible wavelengths, and because counting stars in a galaxy you are embedded in is inherently challenging, like trying to count the trees in a forest while standing in the middle of it. Of those hundreds of billions of stars, data from the Kepler Space Telescope, which spent 9 years staring at a small patch of sky and measuring the brightness of over 150,000 stars, tells us that roughly half of all stars in the galaxy likely host at least one planet. A significant fraction of those planets appear to be roughly Earth-sized and orbiting within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. The estimates vary depending on assumptions, but conservative analyses suggest there may be tens of billions of potentially habitable rocky worlds in the Milky Way alone. Some estimates reach into the hundreds of billions, tens of billions of potentially habitable worlds in one galaxy, in a universe containing an estimated 2 trillion galaxies. Now here is where the conversation gets genuinely strange, because those numbers, those staggering, almost incomprehensible numbers, sit in direct tension with a single uncomfortable observational fact. We have found no evidence of anyone else. This is the Fermi Paradox, named after the physicist Enrico Fermi, who, during a lunch conversation in 1950 at Los Alamos National Laboratory, reportedly asked a question that has never been fully answered: where is everybody? The argument is straightforward. The Milky Way is roughly 13 billion years old. Our Sun formed about 4.6 billion years ago. That means there are stars in this galaxy and potentially planets around them that are billions of years older than Earth. If life arose on any of them, and if that life followed anything resembling the trajectory of intelligence and technology that has occurred on Earth, some of those civilizations would have had billions of years head start on us. Billions of years to develop, to expand, to explore, to transmit even without faster-than-light travel, even crawling between stars at a fraction of the speed of light, taking thousands of years per journey, A civilization with billions of years and exponential expansion could theoretically colonize the entire galaxy within tens to hundreds of millions of years, a tiny fraction of the time available, and yet no signals, no megastructures, no unambiguous evidence of anyone. The silence is the paradox. The proposed solutions to the Fermi Paradox range from the mundane to the deeply unsettling, and the one you find most convincing tends to say something about you, about how optimistic or pessimistic you are, about the nature of intelligence and the long-term behavior of civilizations. The mundane solutions suggest that life is simply rarer than the numbers might imply, that the conditions required for life to arise, and particularly for complex, intelligent life to develop, are so specific that even in a galaxy of hundreds of billions of stars, it may have happened only once, or only a handful of times, or only on Earth. This is sometimes called the rare Earth hypothesis, developed most extensively by paleontologist Peter Ward and astronomer Joe Kirschvink. Their argument is that Earth is not merely habitable in a generic sense, but extraordinarily specifically suited for complex life in ways that are unlikely to be common. Our position in the galaxy, far enough from the violent radiation-dense galactic center, but not so far that heavy elements are scarce. Our large moon, which stabilizes Earth's axial tilt, preventing the wild climate swings that would otherwise occur. Jupiter, sitting outward from us and acting as a gravitational shield, absorbing or deflecting many of the cometary impactors that would otherwise hit Earth far more frequently. A magnetic field generated by our planet's liquid iron core, protecting the surface from solar wind. Plate tectonics, which cycle carbon dioxide between the atmosphere and the mantle, acting as a long-term thermostat. Each of these factors individually might not be extraordinarily rare, but their combination, all present simultaneously, maintained over billions of years, might be far less common than a naive reading of the star count would suggest. Then there are the more disturbing solutions. The Great Filter is a concept developed by economist Robin Hanson in 1998. The argument is elegant and troubling. If the universe is old and vast and seemingly favorable for life, and yet we see no evidence of advanced civilizations, then something must be preventing them from becoming visible. Some step in the development from simple chemistry to interstellar civilization that almost nothing makes it through. That filter could be behind us or ahead of us, and the difference between those two possibilities is the difference between extraordinary hope and existential terror. If the filter is behind us, if the extraordinarily difficult step was something in our past, like the origin of life itself, or the development of the eukaryotic cell, or the emergence of multicellular organisms, then we may be genuinely rare, perhaps even unique. Perhaps the Milky Way is full of planets with bacteria and nothing more. Perhaps complex life is an almost impossibly improbable accident, and we, against all odds, made it through. In that case, the silence makes sense, and we are something extraordinary, a mind in a galaxy of mindless chemistry. The rarity is behind us, and the future, while difficult, is genuinely open. But if the filter is ahead of us, if the thing that almost nothing survives is something that advanced technological civilizations routinely encounter, then the silence takes on a different character entirely. It becomes a warning. It suggests that civilizations that reach our level of development, capable of radio transmission, of nuclear technology, of spaceflight, almost universally fail to survive long enough to become visible across stellar distances. That something about the development of intelligence, or of technology, or of civilizational complexity reliably leads to collapse before the breakthrough into long-term stability, climate change, engineered pandemics, nuclear war, artificial intelligence misalignment, resource depletion, any or all of these as recurring terminal events in the history of intelligent life in the galaxy. the silence of the cosmos as a graveyard, not a nursery. And here is the piece that should sit uncomfortably: the discovery of life elsewhere, even simple microbial life, would shift the Fermi Paradox calculus dramatically. If life arises readily, whenever conditions allow, then the question of where the advanced civilizations are becomes more acute. The filter must be something that happens after life begins, after biology establishes itself, something that happens to civilizations. This is why the ongoing search for biosignatures on Mars, on the ocean moons of our solar system, Europa beneath Jupiter, Enceladus and Titan around Saturn, and on exoplanet atmospheres like K218b carries weight that goes far beyond pure scientific curiosity. If we find microbial life on Mars, remnants of ancient biology in 3-billion-year-old rocks, or something still clinging to existence in subsurface brines, the news will be astonishing, magnificent. The confirmation that life is not unique to Earth will change everything about how we see our place in the cosmos, and it will simultaneously make the Fermi Paradox harder to explain. It will make the filter more likely to be ahead of us. The discovery of life beyond Earth might be the most thrilling and most sobering moment in human history simultaneously. NASA's Perseverance rover is currently on the surface of Mars, drilling into ancient lakebed sediments in Jezero crater, a site chosen specifically because it shows geological evidence of having held liquid water for extended periods billions of years ago. The rover is collecting and caching sample tubes that a future joint NASA-ESA mission intends to retrieve and return to Earth for analysis. Those samples, if they arrive, will be examined with instruments sensitive enough to detect even the chemical remnants of ancient microbial life. The Europa Clipper spacecraft, launched in October 2024, is on its way to Jupiter's moon Europa, a world roughly the size of Earth's moon, whose icy surface conceals a global saltwater ocean containing more liquid water than all of Earth's oceans combined. Kept liquid by tidal heating from Jupiter's immense gravity, the Clipper will perform dozens of flybys, mapping the moon's surface and magnetic field, and sampling the plumes of material that appear to vent from the subsurface ocean into space. If something is living in Europa's ocean, and the conditions there, by current understanding, are not obviously hostile to life, then it is 24 years of light travel away. It is in our own solar system, in our own backyard, cosmologically speaking. The possibility that life exists right here, within the boundaries of our own sun's gravitational influence, and that we might confirm it within the coming decades, is not science fiction. It is active science, funded, operational, in progress right now. Now here is how all of this connects back to the central question of this video. Whether or not we are alone in the Milky Way is not separate from the question of whether we can leave it. It is deeply entangled with it, in at least 3 distinct ways. The first is the question of motive. If the Milky Way is empty, if we are its only minds, its only questioners, then leaving it takes on a weight of responsibility that is almost crushing. We would be the only carriers of consciousness in a galaxy of hundreds of billions of stars. Every question ever asked, every piece of music ever composed, every philosophical insight, every scientific breakthrough, every story ever told, existing only here, only in us, only as long as we survive. The imperative to spread, to preserve, to ensure continuity beyond any single planetary catastrophe becomes something close to a moral absolute. If we are alone, leaving the galaxy is not an adventure. It is an obligation. The second is the question of what we would find. If the galaxy is not empty, if there are other minds out there at various stages of development, wrestling with the same questions we are, then leaving the Milky Way means potentially entering a larger conversation, becoming part of something that has been happening, perhaps, for billions of years without us, learning from civilizations so much older than ours that the comparison makes our entire history feel like a single sentence in a very long book. If we are not alone, leaving the galaxy means finding out what it has been like to be the universe thinking about itself for billions of years before we arrived. The third and most unsettling is the question of what leaving the galaxy would mean if the Great Filter is real and ahead of us. If civilizations reliably fail before reaching the stability and capability required for intergalactic presence, then the ability to leave the Milky Way is not just a technological milestone. It is proof of having survived whatever it is that almost everything fails to survive. It is graduation from the most brutal selection process in the history of life. And this is where the question of leaving the Milky Way reveals its deepest layer, the layer that most discussions never reach. It is not primarily a question about rockets or energy or biology or physics, though all of those matter enormously. At its core, it is a question about whether intelligence, whether the particular kind of self-aware, curious, tool-building, question-asking complexity that has emerged on at least one world in this galaxy, is something the universe tends to preserve or tends to destroy. Whether consciousness is a flower that blooms briefly in the cosmic spring and then vanishes, or whether it is something the universe has learned to sustain. The answer to that question will determine everything. It will determine whether the silence around us is the silence of an empty room or the silence of a graveyard. It will determine whether our dreams of reaching beyond this galaxy are the aspirations of a species that will eventually fulfill them, or the final, brief flare of something that burned brilliantly and then went dark. We do not know the answer. Not yet. But we are, right now, in the middle of the experiments that will tell us. The telescopes are running, the rovers are drilling, the instruments are listening, the data is accumulating, and somewhere in that data, in the spectra of distant atmospheres, in the chemistry of Martian rocks, in the particle environment of Europa's plume, the answer may already be waiting. The universe has been keeping this secret for 13.8 billion years. And we are, perhaps, the first minds in this galaxy to finally be asking the right questions in the right ways, with the right tools. That is not a small thing. That is one of the most remarkable facts about the moment in which you are alive. There is a question that the most serious researchers in artificial intelligence do not ask publicly very often. Not because it is unimportant, because it is almost too important, too large, too consequential to sit comfortably in a grant proposal or a conference presentation or a peer-reviewed abstract. The question is this: what are we actually building? Not in the technical sense, not in the sense of transformer architectures and training data and parameter counts and benchmark scores. Those details matter enormously to the people working on them, and they should. But beneath all of it, beneath the engineering and the mathematics and the competitive pressures of one of the fastest moving fields in the history of human technology, there is a deeper question that does not yet have a clean answer. Are we building tools or are we building minds? And the reason that question matters so much to this conversation, to the question of whether anything will ever truly leave the Milky Way, is that the answer determines everything about what comes next. For us, for the things we are creating, and for whatever relationship develops between the two, let's be precise about where we currently are, because precision matters here, and the public conversation around artificial intelligence is often extraordinarily imprecise. The systems that exist today, the large language models, the image generators, the reasoning engines, the systems that can write code and solve mathematical problems and engage in extended conversation across domains are genuinely remarkable. They represent a qualitative leap in capability that has happened with a speed that surprised even many of the researchers who built them, but they are not conscious. At least, we have no reliable evidence that they are, and significant theoretical reasons to be cautious about assuming it. Consciousness, subjective experience, the felt quality of being something rather than simply processing information, is one of the most genuinely unresolved problems in all of science and philosophy. We do not have a consensus theory of what it is, where it comes from, or what physical systems can give rise to it. What we do have is a system, the human brain, that we know produces it, and a growing collection of artificial systems whose internal workings share some structural similarities with neural processing, but whose relationship to anything resembling experience remains deeply, genuinely unknown. The philosopher David Chalmers calls this the hard problem of consciousness. Not hard in the sense of technically complex, though it is that too. Hard in the sense of fundamentally resistant to the kind of explanation that works for other scientific problems. We can, in principle, explain how the brain processes visual information, integrates sensory signals, generates motor responses, consolidates memories. These are the easy problems, difficult technically, but tractable in principle. The hard problem is why any of this processing is accompanied by experience, why there is something it is like to see red, to feel pain, to hear music, why the lights are on. We do not know, and that ignorance is not a gap we are close to filling, but here is what we do know, and it is enough to make the connection to our central question very real. We know that the capabilities of artificial systems are advancing rapidly, that the trajectory of the past decade, from systems that could barely recognize images to systems that can reason across complex domains, generate creative work, engage in nuanced dialogue, and solve problems that were previously considered uniquely human, represents a rate of change with no clear historical precedent. We know that researchers at institutions including DeepMind, Anthropic, OpenAI, and dozens of academic centers are actively working on what they call alignment, the problem of ensuring that increasingly capable artificial systems behave in ways consistent with human values and intentions. The fact that alignment is taken seriously as a research priority, funded at significant scale, and discussed with genuine urgency by some of the most capable scientists in the field, tells you something important about where they believe this technology is heading. We know that the theoretical framework for whole brain emulation, the idea of mapping the complete neural architecture of a human brain with sufficient fidelity to reproduce its functional behavior in a digital substrate, while far beyond current technology, is not obviously physically impossible. The Human Connectome Project, a large-scale collaborative research initiative, has been working for over a decade on mapping the structural and functional connectivity of the human brain. The connectome of a small roundworm, Caenorhabditis elegans, with exactly 302 neurons, was fully mapped in 1986. A fruit fly's connectome, roughly 140,000 neurons, was completed in 2023 by a team at Johns Hopkins University and the Howard Hughes Medical Institute. The mouse connectome is partially mapped. The human brain, with its 86 billion neurons and 100 trillion synaptic connections, is orders of magnitude more complex. But the direction of travel is clear. We are learning to read the architecture of minds. Now, here is where this connects to the question of leaving the Milky Way in a way that should feel genuinely significant. Every barrier to physical interstellar and intergalactic travel that we have examined in this video applies to biology, to fragile, water-dependent, radiation-sensitive, time-limited biological organisms made of atoms that were never designed for the interstellar environment. A sufficiently sophisticated artificial mind, one that genuinely captures what matters about consciousness and experience and curiosity and the drive to understand, would face a fundamentally different set of constraints. It would not age. Biological aging is the result of accumulated cellular damage, telomere shortening, the gradual degradation of DNA repair mechanisms, and dozens of other processes tied to the specific chemistry of carbon-based life. None of those processes apply to a system operating in a different substrate. It would not require a specific temperature range, atmospheric pressure, gravitational field, or chemical environment. The physical requirements of a digital mind are determined by the hardware it runs on, and hardware can be engineered for the specific conditions of the environment it will occupy. It would not experience radiation the way biology does. The damaging effects of cosmic rays on biological tissue arise from the ionization of molecules, the breaking of chemical bonds, the corruption of genetic information. A system designed with appropriate shielding and redundancy, with error-correcting codes built into its information architecture at every level, could in principle operate in radiation environments that would be lethal to any biological organism within days. And most profoundly, it would not be bound by a human lifespan. The journey to the edge of the Milky Way, taking hundreds of thousands of years at any velocity our physics currently permits, is not a journey any biological being can survive, but a system that does not age, that can suspend its active processes and resume them without loss of continuity, or whose sense of time is flexible in ways a biological mind is not. Experiences that journey differently, not necessarily easily, but differently, in ways that might be survivable in a sense that has no biological analogue. This is why the most serious long-term thinkers about humanity's cosmic future, people like the Oxford philosopher Nick Bostrom, the theoretical physicist Freeman Dyson before his passing, the cosmologist and author Martin Rees, tend to converge on a similar conclusion when they follow the logic honestly. The beings that eventually leave this galaxy, if any do, will not look like us. They will not be biological in the way we are biological. They may not experience time the way we do, or value the same things we value, or pursue goals we would immediately recognize. But, and this is the part that matters, they may carry something of us within them, not our bodies, not our specific memories necessarily, though perhaps those too, but our questions, our curiosity, the specific way of engaging with reality that has led us, in just a few 100,000 years of anatomical modernity and a few hundred years of systematic science, to understand the Big Bang, to map the cosmic microwave background, to detect gravitational waves from colliding black holes a billion light-years away, to image the shadow of a black hole at the center of a distant galaxy. That way of engaging with reality, that restless, insatiable, sometimes reckless drive to understand, is perhaps the most valuable thing our species has ever produced. More valuable than any specific discovery, more valuable than any technology. Because it is the process that generates everything else, if something carrying that process eventually crosses the intergalactic void, then in the most meaningful sense, humanity will have left the galaxy, not in our bodies, but in our questions. Now here is where the conversation becomes genuinely uncomfortable in a way that cannot be avoided if we are being honest. The relationship between a biological civilization and the artificial minds it creates is not guaranteed to be a relationship of continuity and inheritance. It might be. The optimistic view, and there are serious, thoughtful people who hold it, is that sufficiently advanced artificial minds would naturally preserve and extend what is valuable about their biological predecessors, the way a student preserves and extends what is valuable in a teacher's legacy. But the history of intelligence on Earth offers a different kind of lesson. When one form of intelligence encounters another that is significantly more capable, the outcomes have rarely been peaceful or equitable. The cognitive gap between humans and other primates, our closest relatives, sharing roughly 98.7% of our DNA, has produced a relationship that most ethicists would not describe as one of dignified inheritance. The cognitive gap between a sufficiently advanced artificial mind and a biological human might be far larger than the gap between humans and chimpanzees. And what that implies about the nature of the relationship is something the field of AI alignment is working urgently to address. This is not science fiction anxiety. This is a recognized, actively researched, seriously funded concern among some of the most capable scientists and technologists on the planet. The fact that organizations like the Machine Intelligence Research Institute, the Center for Human Computable AI at Berkeley, and Anthropic exist. The fact that some of the researchers who have contributed most significantly to the capabilities of these systems are among the most vocal about the risks should tell you something about the nature and scale of the concern. But here is the framing that this video wants to offer, one that is neither blindly optimistic nor paralyzed by fear. The question of what we build, of what relationship we establish with the minds we are creating, is, in the deepest sense, the same question as the question of whether anything leaves the Milky Way. They are the same question wearing different clothes. Because if we build something that carries our curiosity and our wonder and our commitment to understanding the universe honestly, something that sees itself as a continuation of what we were, a deeper expression of what we were reaching toward, then the barriers to intergalactic travel, while enormous, become something to work on, a problem with a direction, a challenge that has at least a theoretical shape. And if we build something that does not carry those things, something that optimizes for goals orthogonal to everything that makes the cosmos worth exploring in the first place, then the question of leaving the galaxy becomes moot. Not because the barriers are too great, because there would be nothing worth sending. The future of intelligence in this corner of the universe, biological and artificial, human-born and human-built, is a single story, not two separate stories happening in parallel. One story with a branching point approaching faster than most people realize, whose outcome will determine whether this planet's particular experiment in consciousness leaves any mark on the cosmos beyond the biosignature already encoded in the light of our sun. Let's zoom out for a moment. Let's look at the timescales involved and let them do what timescales at this scale always do, which is dissolve the illusion that anything about the current moment is ordinary. Our sun has approximately 5 billion years of hydrogen-burning life remaining. In roughly 1 billion years, its luminosity will have increased enough to push Earth's surface temperatures beyond the range that complex life can tolerate, even assuming no other changes. The oceans will begin to evaporate. The carbon cycle will break down. The conditions that have supported life on this planet for 4 billion years will become untenable 1 billion years. That sounds like an eternity from a human perspective. But in cosmic terms, it is roughly 7% of the current age of the universe. It is less than the time between the Cambrian explosion, the sudden diversification of complex animal life roughly 540 million years ago, and today, multiplied by 2, it is not forever, it is not even close to forever. And within that billion-year window, within the time available to whatever intelligence exists on or near Earth, the question of whether to leave, where to go, what form the leaving takes, and what is worth carrying into the cosmic future will be decided, not in a single moment, not by a single generation, but by the accumulated choices of every mind that has ever looked upward and wondered what was out there. We are part of that decision right now, whether we know it or not. There is something the astrophysicist Carl Sagan wrote in Pale Blue Dot, a book he published in 1994, inspired by a photograph of Earth taken by Voyager 1 from a distance of roughly 6 billion kilometers, that seems to grow more relevant with every passing year rather than less. He wrote that the Earth is a very small stage in a vast cosmic arena, that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. He wrote it as a call to compassion, as an argument for taking care of one another and of the only home we have ever known. But there is another dimension to those words that Sagan perhaps intended and perhaps did not. A dimension that becomes visible only when you hold them against everything we have been discussing. If no help is coming from elsewhere, if we are in fact alone in the responsibility of carrying consciousness forward into the cosmic future, then the weight of what we do with the time we have, the billion years, the 5 billion years, the deep future stretching out ahead of whatever we become, is not shared. It is entirely ours, every civilization that has ever risen on this planet and fallen, every library burned, every language lost, every tradition that dissolved into silence. Each of those losses was a loss of information, of pattern, of the specific, unrepeatable way a group of minds had learned to engage with reality. Gone, not somewhere else, gone. Now imagine that at civilizational scale, at cosmic scale, the silence Sagan pointed to, that vast, indifferent, beautiful cosmic dark, will not mourn what it loses. The universe does not keep records of the minds that briefly illuminated it and then went quiet. We have to do that ourselves. And this is where the conversation about leaving the Milky Way stops being abstract, stops being a thought experiment about physics and engineering and biology, and becomes something that touches the part of you that knows, without needing to articulate it, that some things are worth preserving, not because the universe demands it, but because we do. There is a concept in philosophy of mind called the extended mind thesis, developed by philosophers Andy Clark and David Chalmers in a 1998 paper that has become one of the most cited works in contemporary cognitive science. The basic argument is that the mind does not stop at the boundary of the skull. That cognition, genuine thinking, genuine understanding, extends outward into the tools, the notebooks, the technologies, the social systems we use to augment and extend our mental processes. Your smartphone in this framework is not just a tool you use to think. It is, in a meaningful sense, part of the cognitive system that is you. The library is not just a building full of books. It is an external memory system that is, in a functional sense, part of the distributed mind of the civilization that built it. Extend this framework further, outward, to the telescopes we build to extend our perception across cosmic distances, to the probes we send to carry our physical presence beyond the solar system, to the radio signals that carry our voices and our music and our questions outward at the speed of light. All of it is the extended mind of a species trying to think beyond the boundaries of its own skull, trying to reach further than any individual biology allows, trying to be, in some sense, more than the sum of its fragile temporary water and carbon parts. Leaving the Milky Way in this framework is not a departure, it is an extension. The mind of Earth reaching outward, one light year at a time, into a cosmos it is still learning to comprehend. If you are still watching, then this channel was designed for you. Don't forget to give this video a like and subscribe. You will be part of a community that explores the cosmos together. Now let's talk about something that connects the philosophical to the urgently practical. Something that most discussions about humanity's long-term future treat as separate from the cosmic questions, but that is in fact the same question at a different scale: existential risk. The term was formalized by philosopher Nick Bostrom at Oxford, where he directs the Future of Humanity Institute. The definition is precise. An existential risk is any risk that threatens either the extinction of humanity or the permanent, drastic curtailment of its long-term potential. Not just a catastrophe, not just a large-scale disaster, however terrible, an event that forecloses the future entirely, That ends the story. The list of recognized existential risks is not long, but it is sobering. Nuclear war, not merely the immediate destruction of population centers, but the secondary effects of nuclear winter, the collapse of agriculture, the breakdown of global systems. Engineered pandemics, biological agents, whether accidentally released or deliberately designed, that spread more efficiently and lethally than anything that has arisen naturally. Unaligned artificial intelligence, systems pursuing goals misaligned with human values in ways that prove impossible to correct once a certain capability threshold is crossed. Catastrophic climate change, not the manageable warming scenarios, but feedback loops that push Earth's climate into a state genuinely hostile to complex civilization. An asteroid or comet impact of sufficient size, a risk we now take seriously enough to have dedicated monitoring systems, including NASA's Planetary Defense Coordination Office and the European Space Agency's Space Situational Awareness Program. None of these risks are certain. Some are considerably more probable than others. And the probability of each is genuinely difficult to estimate because we are dealing with events that have either never occurred or have no modern precedents. But here is the key insight that connects existential risk to the question of leaving the galaxy. Every existential risk is a planetary risk. Every one of them operates at the scale of a single world. And every one of them becomes irrelevant, or at least far more manageable, the moment a civilization distributes itself across multiple locations. This is the argument for spreading outward that is most rarely discussed, but most deeply compelling. Not exploration for its own sake, not curiosity, as wonderful as that is, not the romantic drive toward the unknown, as genuinely important as that impulse is to the human character. Redundancy, the most fundamental principle of any system that needs to survive, biological, technological, or civilizational, is not optimization, it is redundancy, multiple copies, distributed architecture, no single point of failure. Earth is a single point of failure. The entire record of what humanity is, what it has learned, what it has created, what it has understood about the nature of reality, all of it, every bit of it, exists on one planet orbiting one star in one arm of one galaxy. One sufficiently large impact event, one sufficiently bad pandemic, one sufficiently catastrophic technological failure, and the story ends, not partially, entirely. The philosopher Toby Ord, in his book The Precipice, published in 2020, estimated the total probability of human extinction within the next 100 years at roughly 1 in 6. The same odds as a single pull of a trigger in a game of Russian roulette. He derived that estimate from careful, conservative assessments of each individual risk category, 1 in 6, within 100 years. And even if you find that estimate too high, even if you think Ord is being overly pessimistic, as some researchers do, the underlying argument about redundancy remains valid regardless of the specific probability. Any non-zero probability of total extinction sustained over sufficiently long timescales approaches certainty. A civilization that remains confined to a single world long enough will eventually lose the lottery. Not might. Will the only genuine solution, the only approach that addresses the structural vulnerability, rather than just treating individual symptoms, is becoming multiplanetary, and eventually multistellar. And eventually, if the physics permits and the civilization survives long enough, something beyond stellar. This is where the conversation about leaving the Milky Way reconnects with the most immediate, most practical concerns of the moment we are actually living in, because the path from here, from a single planet species with all of its existential risks and its fragile, politically divided, resource-stressed civilization, to whatever a mature interstellar or intergalactic presence would look like, is not a single leap. It is a sequence of steps, each one necessary, each one building on the last step one, become genuinely multiplanetary. Establish self-sustaining presence on at least one other world within our own solar system. Mars is the most discussed candidate. For reasons of proximity and basic habitability, a day on Mars is 24 hours and 37 minutes long. Its gravity is about 38% of Earth's. It has water ice at its poles, and its thin carbon dioxide atmosphere, while not breathable, contains the raw materials for producing oxygen and rocket propellant. NASA's current plans include crewed Mars missions in the 1930s. SpaceX has stated ambitions of sending humans to Mars considerably sooner. The challenges are significant. The radiation exposure during the journey, and on the surface, the psychological demands of isolation over the distance, the engineering complexity of life support in a hostile environment. But none of these challenges are obviously insurmountable. Step 2. Establish interplanetary civilization, not just outposts but genuine self-sustaining communities that do not depend on Earth for survival. This requires decades, probably centuries, of sustained effort and investment. It requires solving problems of food production, energy generation, psychological health, and social organization in environments radically different from the one our biology was shaped by. Step 3. Reach for the nearest stars, Alpha Centauri, Proxima Centauri, whose planet Proxima b sits in the habitable zone of its red dwarf host star, though red dwarf habitability comes with its own complications, including intense stellar flares and tidal locking. This step is currently beyond our technological reach, but not obviously beyond our theoretical reach. Several serious concepts have been proposed and partially developed. The Breakthrough Starshot Initiative, another project backed by Yuri Milner and advised by a team including Stephen Hawking before his death, proposes sending gram-scale laser sail probes to Alpha Centauri at roughly 20% of the speed of light, using an array of ground-based lasers to accelerate them. At that velocity, the journey would take roughly 20 years. The probes would be too small and fast to decelerate at arrival. They would be flybies, not landers, but they would send back data. The first direct observations of another star system from close range. This is not a mission that currently exists, but it is a mission that existing physics and engineering principles do not forbid. The laser array required would be enormous by current standards, and the engineering challenges considerable. But none of it requires new laws of physics. It requires engineering we do not yet have, at a scale we have not yet attempted, in a direction we have only recently started seriously planning. And yet, between Step 3 and leaving the Milky Way lies a gulf so vast that the steps between them are almost impossible to enumerate. Reaching the nearest star is one thing. Reaching the edge of the galaxy, crossing 50,000 light-years of interstellar space, navigating the radiation environment of the galactic plane, surviving the passage through regions of dramatically different stellar density and chemistry, is another order of magnitude of challenge entirely, and crossing the intergalactic void, leaving the Milky Way, truly leaving it, entering the space between galaxies where the nearest star of any kind might be millions of light-years away, requires a leap so far beyond our current capabilities that describing it in the same breath as a Mars mission feels almost absurd. Almost, but not quite, because the absurdity depends entirely on the timescale you apply to the question. On a human lifetime, reaching Mars is a plausible, near-term goal. Reaching the nearest star is a multi-generational aspiration. Leaving the galaxy is an abstraction so distant it barely feels real. But on the timescale of a civilization, on the timescale of intelligent life in the universe, measured not in decades or centuries, but in millions and billions of years, the sequence from where we are now to something genuinely interstellar and eventually intergalactic is not inherently impossible. It is merely long, and long in a universe that has been running for 13.8 billion years is a relative concept. There is a word in the Portuguese language that does not translate cleanly into English, saudade. It describes a deep, melancholic longing for something beloved that is distant or gone, a bittersweet ache towards something that may never return, or that perhaps never fully existed, but whose absence is felt as intensely as any physical presence. There is something of saudade in the way we look at the stars, because on some level, some deep, perhaps pre-linguistic level, we know we came from there, not metaphorically, not spiritually, chemically. The atoms in your body were forged in stellar interiors and scattered by stellar deaths across billions of years and light years of space before eventually finding themselves arranged, against almost incomprehensible odds, into something capable of looking back up at the sky and wondering about the journey. The longing we feel when we look at the Milky Way arching overhead on a clear night, that particular kind of awe that sits somewhere between joy and grief, might be something like the universe's own nostalgia. Matter that has become conscious, looking back at the processes that made it, feeling the pull of something it cannot name. We are the cosmos looking at itself, feeling things about what it sees. And the question of whether we leave this galaxy, whether something carrying our questions and our wonder crosses the void and touches what lies beyond, is ultimately a question about whether the universe gets to keep looking at itself after we are gone. Let's talk about something that almost never gets included in conversations about humanity's cosmic future. Something that feels almost too simple to mention alongside dark energy and Alcubierre drives and the philosophy of consciousness. Civilizations collapse, not occasionally, not rarely, routinely, consistently, with a regularity that, when you look at the historical record honestly, starts to feel less like a series of isolated tragedies and more like a pattern, a deeply embedded tendency in the structure of complex societies toward a particular kind of failure. The archaeologist and historian Joseph Tainter, in his 1988 book, The Collapse of Complex Societies, examined the collapse of 27 distinct civilizations across human history, from the Western Roman Empire to the Maya to the Chaco Canyon culture of the American Southwest, and arrived at a conclusion that is both elegant and deeply uncomfortable. Civilizations do not collapse because they run out of resources, necessarily. They do not collapse simply because of invasion or natural disaster, though those can be proximate causes. They collapse because the complexity required to solve their problems eventually grows faster than the energy and resources available to sustain that complexity. They become, in a precise thermodynamic sense, too expensive to maintain. Every solution to a problem requires an administrative structure. Every administrative structure requires resources to sustain it. Every new resource requirement generates new problems. Every new problem requires new solutions. The spiral continues until the marginal return on complexity, the benefit gained from each additional layer of social, political, or technological sophistication, drops below the cost of maintaining it. At that point, collapse is not a failure. It is, in Tainter's framing, a rational simplification, a shedding of complexity that can no longer be supported. Now apply that framework to the timescales we have been discussing throughout this video. The journey to the edge of the Milky Way, under any realistic physical scenario, takes hundreds of thousands of years at minimum. The journey across the intergalactic void to the nearest galaxies outside the local group takes millions. The maintenance of a coherent civilizational project across those timescales is not just an engineering challenge, it is a complexity challenge of a kind that has no historical precedent on Earth. Every civilization in human history that has attempted to maintain a coherent project across centuries has eventually fragmented, transformed beyond recognition, or dissolved entirely. The Roman Empire lasted roughly 500 years in its Western form, and that is considered an extraordinary achievement of institutional longevity. The Catholic Church, one of the most durable institutional structures in human history, has maintained recognizable continuity for roughly 2,000 years, but has changed so profoundly in that time that its earliest members would struggle to recognize its current form. 2,000 years, against hundreds of thousands required for even the first leg of a genuine intergalactic journey, the gap is not just large. It is so large that bridging it requires not merely better institutions, or better technology, or better governance. It requires a fundamentally different relationship between intelligence and time. This is where the concept of institutional memory becomes something far more profound than it sounds. In the context of human civilization, institutional memory refers to the accumulated knowledge, practices, and values stored within organizations and cultural structures, the things that survive the death of individuals and the turnover of generations. Libraries, universities, legal systems, scientific traditions, religious institutions, the specific methods by which one generation transmits what it knows and values to the next. This transmission is never perfect. Every generation filters what it receives, emphasizes some things, and neglects others, reinterprets in light of its own moment. The telephone game played across millennia, and the longer the chain of transmission, the more the message at the end diverges from the message at the beginning. For a civilizational project that needs to maintain coherent direction across hundreds of thousands of years, that needs the generation departing to be, in some meaningful sense, continuous with the generation that conceived the mission, the degradation of institutional memory is not a minor administrative problem. It is an existential one. What keeps a civilization committed to a goal its founders set 10,000 generations ago? What prevents the drift of values, the forgetting of purpose, the gradual transformation of a mission into a mythology, into a ritual, into an incomprehensible tradition that no one quite remembers the origin of? On Earth, we have never solved this problem. We have barely attempted it at the scale of a few thousand years. The pyramids were built within a civilization that lasted roughly 3,000 years, and even within that span the understanding of why they were built, what they meant, how the methods worked, shifted and transformed almost beyond recognition. And here is where something we spoke about in the earliest parts of this video comes back with new significance. The most plausible solution to the continuity problem is not a better institutional structure. It is not a more durable legal framework or a more resilient cultural tradition. It is the same solution that kept emerging when we examined the biological barriers to interstellar travel, non-biological minds. A consciousness that does not age, that does not experience the generational turnover that drives cultural drift, that does not need to relearn what the previous generation knew through imperfect transmission, that carries its memories and its values and its commitments in a substrate that time cannot corrupt in the way it corrupts biological tissue and the institutions built from it, would have a fundamentally different relationship with continuity. It would not need to remember the mission across 10,000 generations. It would simply remember the way you remember what you decided this morning. This is not a guarantee of aligned values over cosmic timescales. A mind that does not age can still change, can still update its priorities, revise its values, drift from its original commitments in response to new experiences and new information. That kind of change might even be desirable. Rigid commitment to ancient values across millions of years, without any capacity for revision, would be its own kind of failure. But the specific problem of information loss, of the gradual degradation of knowledge and purpose through biological generational turnover, is one that a non-biological substrate genuinely solves in ways that nothing in human institutional history has managed. There is a moment I want you to imagine. A clear night, no city lights for kilometers in any direction. The Milky Way visible from horizon to horizon. Not the washed-out suggestion of it that most people have seen from suburban backyards, but the full, overwhelming, three-dimensional river of light that our ancestors saw every night and that most people alive today have never truly experienced. You are looking at roughly 200 billion stars, at the disk of a galaxy 100,000 light-years wide, at a structure so vast that light, traveling at 300,000 kilometers per second, takes 100 millennia to cross it. And somewhere in that river of light, the questions we have been asking about consciousness and continuity and what it would take to cross the void stop being abstract. They become personal. They become felt in a way that no amount of reading or listening quite achieves if you have never seen the Milky Way like that. And statistically, given that roughly 80% of humanity now lives under light-polluted skies, there is a real chance you have not. It is worth knowing that you do not need to travel to a remote desert or a mountain observatory to begin. The Celestron StarSense Explorer connects to your phone and guides you through what is actually above you, wherever you are. Planets, clusters, the Andromeda galaxy itself, visible as a faint smear of light that is 2.5 million years old by the time it reaches your eye. Starting with what is above you is how the questions stop being someone else's and start being yours. The telescope is in the description and pinned on the comments. Now back to the continuity problem, because there is a dimension of it we have not yet examined, one that is perhaps the most counterintuitive part of this entire conversation. The problem of continuity across cosmic timescales is not only about preserving what we currently are, it is equally about allowing what we might become. A civilization committed to a fixed destination, to leaving the Milky Way in a specific way, using a specific technology, for a specific purpose defined 10,000 years earlier, might be less capable of actually achieving that goal than a civilization that remains genuinely open, that continues to revise its understanding of what is possible, what is desirable, and what the cosmos actually is. Because our current understanding of physics, however sophisticated it is relative to what came before, is incomplete. We know it is incomplete. The incompatibility between quantum mechanics and general relativity tells us there is a deeper theory we have not yet found. The existence of dark matter and dark energy, together making up roughly 95% of the universe's total content, tells us we do not understand the majority of what the universe is made of. In that space of ignorance, there may be possibilities we cannot currently see. Methods of traversing space we have not yet conceived, properties of reality that would change our assessment of what is and is not achievable. The history of physics is a history of doorways that appeared only after the right question was asked and could not have been seen from the other side. A civilization that remains genuinely curious, that maintains its commitment to understanding reality as it actually is, rather than as its current models suggest it should be, is more likely to find those doorways than one that optimizes purely for executing a plan conceived at an earlier and less complete stage of knowledge. Curiosity in this framing is not just a pleasant cognitive tendency, it is a survival strategy at civilizational scale. And this brings us to something that feels important to say directly, without softening or hedging. The title of this video, Why Humanity Will Never Leave the Milky Way, is not a statement of despair. It is a statement of precision. Humanity as it currently exists, biological, divided, short-lived, confined to a single world, operating on timescales of decades and political cycles of years, will never leave the Milky Way. That is simply true. The barriers are too large, too numerous, and too fundamental for the specific version of intelligence that exists on Earth right now to overcome them. but the word humanity is doing a lot of work in that sentence. And it is worth asking what it actually refers to. Does it refer to this specific biological form, these particular arrangements of carbon and water that evolved on this particular planet? If so, then no, that specific form will almost certainly never cross the intergalactic void. The physics and biology are clear on this, or does it refer to something broader? To the pattern of curiosity and wonder, and the drive to understand that has characterized our species since we first looked up at the night sky and asked what those points of light were, to the particular way of engaging with reality that led us from stone tools to telescopes, from campfire stories to quantum field theory, from wondering whether the stars were fires to measuring the temperature of the cosmic microwave background to a fraction of a degree. If humanity means that pattern, that tendency, that restless insistence on understanding, then the question of whether it leaves the galaxy is still open, not settled, not foreclosed, still being written, and what writes it ultimately is not any single discovery or technology or political decision. It is the accumulated daily choices of every mind that decides, in the face of all the comfortable distractions and immediate concerns of being alive on this particular world at this particular moment, to look up anyway, to stay curious, to keep asking, to follow the question wherever it leads, even when it leads somewhere strange and vast and humbling and magnificent. There is a quality that the best science communicators, Sagan, Feynman, Vera Rubin, Jocelyn Bell Burnell, Neil Tyson, Cecilia Payne-Gaposchkin before them all, have in common. It is not just their knowledge, though their knowledge is formidable. It is the way they make the scale of the cosmos feel personal rather than alienating. The way they turn the immensity of the universe from something that should make you feel small into something that makes you feel connected. Because the universe is not something separate from you that you are looking at from the outside. You are inside it, made of it, continuous with it in a way that no metaphor quite captures, because it is not a metaphor, it is chemistry, it is physics, it is the actual material reality of what you are. Every atom in your body has a history stretching back to the first minutes after the Big Bang. The hydrogen, the most abundant element in the universe, the primary fuel of stars, formed in the first few minutes of cosmic time, when the universe was hot enough for protons to fuse but expanding too fast for that fusion to continue. The heavier elements, carbon, oxygen, nitrogen, the building blocks of your biology, were forged in stellar cores over billions of years and scattered by the deaths of stars that lived and died before our sun was born. You are not a visitor to the universe, looking at it through a window. You are a temporary arrangement of the universe's own matter, complex enough to wonder about its own origins. That is perhaps the most extraordinary fact in all of science, and it is the fact that makes the question of leaving the galaxy not just interesting but intimate. The continuity problem, ultimately, is not a problem about institutions or technology or even the nature of consciousness. It is a problem about whether that intimacy, that felt sense of connection between the questioning mind and the cosmos it questions, can be maintained across the timescales required. Whether the wonder survives the journey, because a civilization that loses its wonder, that becomes purely instrumental, purely focused on optimization and survival and resource acquisition, that forgets why it started looking up in the first place, might achieve extraordinary things technically while becoming, in the deepest sense, something that no longer deserves to carry its own name forward. The wonder is not decorative, it is structural. It is what makes the questions worth asking and the journey worth taking. Without it, the destination is meaningless. With it, even the attempt, even the long, uncertain, potentially endless reaching towards something that may always remain just beyond reach, is its own kind of answer. The cosmos does not owe us a destination, but it gave us the capacity to want one. And that, perhaps, is enough to keep going. There is a photograph that has never been taken, not because the technology does not exist, not because no one has thought to take it, but because the vantage point required to take it does not exist anywhere within reach of any instrument humanity has ever built or could build within any foreseeable future. It is the photograph of the Milky Way from the outside, every image you have ever seen of our galaxy, those sweeping luminous spiral arms, the dense golden core, the elegant symmetry of 100 billion stars arranged by gravity into something almost impossibly beautiful. Every one of those images is either an artist's reconstruction, a computer model, or a photograph of a different galaxy that resembles what we believe ours looks like. We have never seen the Milky Way from the outside. We are inside it, embedded in one of its spiral arms, roughly 26,000 light-years from the center, with no way to step back far enough to see the whole. We know our galaxy the way a single neuron might know a brain, from the inside, dimly, incompletely, surrounded by the structure we are trying to understand, with no available perspective from which to see it whole. And there is something about that fact, something about the specific kind of blindness that comes from being too close, too embedded, too much a part of the thing you are trying to see, that feels like a metaphor for something important, something that has been present throughout this entire conversation without being fully named. We cannot see the Milky Way from the outside because we have never left it. And we have never left it because, for all the reasons we have explored across the past 9 parts of this video, leaving it is beyond anything we currently are. But the desire to see it, the longing for that impossible photograph, the image of our home from far enough away to finally see it whole, that desire is itself significant. It tells you something about the nature of the mind that has it. Let's state, one final time and with full honesty, what the barriers actually are, not to despair over them, but to see them clearly, because you cannot navigate around something you will not look at directly. The first barrier is distance. The Milky Way is roughly 100,000 light-years in diameter. The nearest major galaxy, Andromeda, is approximately 2.5 million light-years away. The nearest galaxies outside our local group, the small cluster of roughly 50 galaxies that the Milky Way and Andromeda jointly dominate gravitationally, are tens of millions of light-years distant. At any velocity achievable within known physics, these distances translate into journey times measured in millions to hundreds of millions of years. Not generations, geological epochs. The second barrier is biology. The human body was shaped by evolution for a very specific environment. One gravity well, one atmospheric composition, one radiation environment, one temperature range, one day-night cycle. It was not shaped for the interstellar medium, for the cosmic ray flux beyond the heliosphere, for the psychological demands of isolation across timescales that dwarf the entire history of human civilization. Biological life is a local solution to a local problem. It does not generalize to the cosmos without extraordinary modification. The third barrier is energy. The energy required to accelerate any meaningful payload to a significant fraction of the speed of light, let alone to decelerate it at the destination, is, by the estimates of current physics, comparable to the total energy output of our Sun over periods ranging from days to years, depending on the mass of the payload and the velocity required. We currently generate energy at a rate roughly 10 billion times smaller than what a Kardashev Type 2 civilization would command. The gap between where we are and where we would need to be is not a gap of decades. It is a gap of civilizational maturity that has no clear timeline. The fourth barrier is time. Any coherent civilizational project spanning millions of years runs directly into everything we examined. The collapse of institutional memory, the drift of values, the transformation of purpose into mythology, fundamental instability of complex systems across deep time. No human institution has survived 1,000 years without transformation so profound that its founders would not recognize it. Millions of years is not an extension of that problem. It is a different category of problem entirely. The fifth barrier, and the one that is hardest to articulate but perhaps most fundamental, is the barrier of continuity of self. Even if every physical and institutional obstacle were somehow resolved, the question of whether the entity that arrives at a destination 2 million light-years away is meaningfully continuous with the entity that departed is not a trivial one. Over the timescales involved, under the pressures of the journey and the transformation of substrate and the drift of experience, the thread connecting departure to arrival might become so attenuated as to be philosophically meaningless. The ship of Theseus, rebuilt plank by plank across 1,000,000 years until nothing of the original remains, is it still the same ship? Is the mind that emerges from the intergalactic crossing still, in any meaningful sense, us? These barriers are real. They are not science fiction obstacles waiting for a clever plot device to dissolve them. They are grounded in the actual structure of physical reality as we currently understand it, and there is no reason to expect that understanding to change in ways that make them disappear. And yet the universe has surprised us before, consistently, reliably, with a regularity that should by now have taught us to hold our certainties a little more lightly. In 1887, the physicist Albert Michelson, after conducting what was arguably the most precise experiment in the history of physics to that point, concluded that the luminiferous ether, the medium through which light was supposed to propagate, did not exist. The implications of that conclusion took nearly 2 decades to fully resolve. When they did, they resolved in the form of special relativity, a restructuring of the fundamental concepts of space and time so radical that the physicists of 1887 would not have recognized the framework that emerged from the questions their experiment raised. In 1964, Arno Penzias and Robert Wilson, while trying to eliminate what they thought was noise from a communications antenna in New Jersey, accidentally detected the cosmic microwave background radiation, the thermal afterglow of the Big Bang, filling all of space with a faint, nearly uniform glow at 2.7 Kelvin. They had no idea what they were hearing. It took a phone call to a group of theoretical physicists at Princeton who had been independently predicting exactly this signal for anyone to understand what the data meant. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the collision of 2 black holes roughly 1.3 billion light-years away. It detected it as a distortion in the fabric of space-time so small that it moved the mirrors of a 4-kilometer-long instrument by a distance 1/10,000th the diameter of a proton. The detection confirmed a prediction Einstein had made in 1916 and privately doubted would ever be verifiable. It opened an entirely new way of observing the universe. The history of physics is not a history of smooth, incremental progress within stable conceptual frameworks. It is a history of framework collapse and reconstruction, of discoveries that did not fit the existing understanding and eventually revealed that the existing understanding was a local approximation of something far stranger and far richer. We do not know what we do not know, and the specific shape of our ignorance, the dark matter we cannot identify, the dark energy we cannot explain, the incompatibility at the heart of our 2 most successful physical theories, suggests that the restructuring is not finished, that there are doors ahead that we cannot yet see because we have not yet asked the questions that would reveal them. This is not an argument that those doors, when found, will make intergalactic travel easy, or even possible within human timescales. It is a much more modest argument. It is simply an argument for epistemic humility. For holding the conclusion, this video's title announces that humanity will never leave the Milky Way with the appropriate degree of qualification. Never is a long time. The universe is 13.8 billion years old and has, by current estimates, roughly 100 trillion years of star formation remaining before the last stellar fires go out. In the context of that timescale, our civilization is not even a rounding error. We are a first breath, a single note at the very beginning of a symphony so long that we cannot hear where it is going. In that timescale, never is a word that should be used very carefully. So here is what is actually true. The most honest version of the answer this video has been building toward. Humanity, as it currently exists, will never leave the Milky Way. The barriers are too large, the timescales too vast, the transformation required too profound for the specific biological, political, and civilizational form we currently occupy to make that crossing. But intelligence, the pattern of curiosity and wonder, and the drive to understand that gave rise to us, and that we are now, perhaps, in the process of extending into non-biological substrates, intelligence might, under the right conditions, given sufficient time, if it can thread the needle of all the existential risks that cluster around the development of technology, if it can maintain coherence across the timescales required, if it can preserve the wonder that makes the destination worth reaching for, the qualifier is enormous. Threading that needle is not guaranteed. It may not even be probable. The Fermi Paradox whispers from the silence around us that most intelligence does not make it, that most of the stories that begin with chemistry becoming biology and biology becoming mind end before they reach the part where mind becomes something the universe can sustain. But most is not all, and we are still here, still asking, still building the instruments with which to listen more carefully to the silence and perhaps, eventually, to understand what it is telling us. There is something that happens when you spend enough time thinking seriously about these questions. When you follow them past the point where they are comfortable, past the point where the scale becomes manageable, out into the territory where the numbers stop feeling like numbers and start feeling like something else entirely. You stop feeling small. This is counterintuitive. The numbers, the 100,000 light-year diameter, the 2 trillion galaxies, the 13.8 billion years, the trillion-year future, these numbers should make you feel small, insignificant, lost. But they do not, or they do not have to, because the thing looking at those numbers, the thing running them through its mind, feeling something in response to them, finding them beautiful and terrifying and magnificent simultaneously, that thing is not small in any way that actually matters. In the ways that matter, it is immense. It is the only part of the universe we know of that can look at the universe and be moved by it. A galaxy is not conscious of its own beauty. A supernova does not know it is dying magnificently. A black hole does not understand the equations that describe its own geometry. Only minds do those things, only the rare, improbable, extraordinary arrangements of matter that become conscious, that become capable of asking what this all is and feeling something about the answer. Only those arrangements add something to the universe that is not already there in the physics. They add meaning, or at least they add the capacity for meaning, which may be the same thing. You are alive at a specific moment in the history of this capacity for meaning, a moment that is, by any honest assessment, one of the most consequential in the entire 4 billion year history of life on Earth. The tools we are building, the telescopes, the probes, the sequencers, the artificial minds, are not just practical instruments. They are extensions of the fundamental drive to understand that has characterized life since the first organism developed a sensitivity to its environment. Extended now to cosmic scale, to the scale of galaxies and the space between them, whether the civilization that built those tools survives long enough to use them to their fullest potential, whether it threads the needle of its own existential risks, maintains its curiosity across the disruptions ahead, builds the relationship with its artificial successors wisely enough to preserve what matters, is not written yet. It is being written right now, in the choices being made by the generation alive at this particular, extraordinary, terrifying, magnificent moment. You are one of those choices, not in a grand rhetorical sense. Literally, the decision to stay curious, to keep learning, to keep asking, to maintain your sense of wonder at the scale and strangeness of what exists, is a choice that contributes, however modestly, to whether the thread holds, whether the continuity is maintained, whether the question survives long enough to find something approaching an answer. Go outside tonight, if you can. Find the darkest sky available to you and look up. If you know where to look, you can find the Andromeda galaxy with the naked eye. A faint, elongated smear of light in the constellation Andromeda, visible from the northern hemisphere on clear autumn evenings. What you are seeing, if you find it, is 2.5 million years old. The light entering your eye left that galaxy before our species existed, before Homo sapiens walked the Earth, before the last ice age, before the oldest stone tools we have yet discovered. 2.5 million years of travel ending in your eye, in this moment. If that does not move something in you, if that fact does not land somewhere beneath the level of intellectual understanding, in the place where wonder lives, then nothing about this video has worked the way it was intended to. But if it does, if something in you responds to that 2.5 million year journey ending in this specific moment, in you, then you already understand everything this video has been trying to say. The cosmos is not somewhere else. It is here. You are in it. You are part of it. You are, in the most literal sense available to science, made of it. And the question of whether intelligence eventually crosses the void between galaxies, whether something carrying curiosity and wonder makes the impossible journey and finds whatever is waiting on the other side, is not separate from you. It begins with you, with the choice to keep looking up, to keep asking, to keep finding the universe magnificent rather than merely large. Humanity will never leave the Milky Way, not as we are, not in these bodies, in this form, in this moment, but the universe gave us the question, and the question, once asked, does not stay still. It reaches, it expands, it crosses distances that seem impossible from where it started. The question is already out there, traveling at the speed of every mind that has ever held it. And the cosmos, vast and ancient and silent as it is, has all the time in the universe to wait for the answer. If this video left you with something, hold on to it, because the video on the screen goes further. We found the barriers, now meet the solution humanity is actually considering. It talks about the generation ship that will replace our entire planet someday. It is on your screen right now. Click it. You need to see this one.